So, hello, it's my pleasure to introduce our next speaker, Aliaksandr Hancharuk. He was born in Belarus, then graduated in 2009 in the Moscow Institute of Physics and Technology. He has obtained PhD in Lyon University under supervision of Thomas Strobl half a year ago in 2023. And since this March, the March of 2024, Aliaksandr is a postdoc at Jilin, how to say it correctly? Sasha, Jilin?
Don't
Jilin?
ask me.
Jilin University in China. So it's my pleasure to introduce him. He will introduce his research interests himself. So the recording started.
Okay, thank you very much for the introduction. So now let me share my screen. Okay, do you see my screen? Hello?
Yes.
Okay, thank you. So in this talk, I will talk about some particular constructions of Koszul-Tate resolutions using decorated trees. And this is based on a joint work with Camille, Laurent-Gengoux, and Thomas Strobl, also on my PhD thesis, but it's still not available online, but I hopefully it will be. So let me maybe start by just giving definition of what is a Koszul-Tate resolution and what's the motivation behind it. So one usually starts, so let O commutative algebra and I inside O a proper ideal, then Koszul-Tate resolution of over I. So the quotient algebra of O modulo I is first, of course, is a resolution of O over I, such that it has a structure of symmetric algebra. So it's a resolution. Resolution A delta, such that A is S of epsilon, so symmetric tensor product of epsilon, where epsilon is O plus epsilon 1 plus epsilon k plus and so on. So this is just graded projective or free sometimes, or module. So in other words, if one just decomposes according to a degree, and also delta, don't forget delta is a graded O derivation. So if one would decompose this according to the degree, then like the first terms looks as follows. So O epsilon 1 here, epsilon 2 plus epsilon 1 epsilon 1. So I write O dot for the symmetric tensor product, and again epsilon 3 plus epsilon 2 plus epsilon 2 on dot epsilon 1 plus epsilon 1 3 times and so on. And of course, the condition that it is a resolution just says that in the homology in the positive degree is in 0, and H0 of delta is just O modulo I. So what's the motivation behind studying such objects? The motivation. So for us, it comes from BFV, Batalin-Fradke-Vilkovisky or Batalin-Vilkovisky construction. I'll allow myself to be a bit lazy for this particular moment, to use a little bit the talk of Alexei Kotov 2 weeks ago, just briefly saying what is this. So the BFE construction is a particular that graded Q-manifold. So I think again, so I refer for the definitions to Alexei's talk just to save time, which happened 2 weeks ago, and such that so one of the properties of the BFE construction that let's call it BFB divided by I plus. So I plus, it was the ideal generated by positively graded generators, is a Koszul-Tate resolution of O over I. So in a sense, it's some particular, again, it's a particular graded Q-manifold. I don't write all the properties that it has, but the point is that its underlying block is a Koszul-Tate resolution of O over I. So hence it has some applications in mathematical or theoretical physics. So I would like to start now just giving examples, known examples. So essentially, in the literature, whenever one wants to learn about examples of Koszul-Tate, there is almost only one example, is when ideal I is generated by a regular sequence. O is Noetherian. No, Noetherian. So I is just, let's write it phi 1, phi k over O. And the condition of being a regular sequence, it just means that each generator's phi j is non-zero divisor of O modulo phi 1 to phi j minus 1. So perhaps you've seen already regular sequences or worked with them, but if not, so just very simple example of what this definition means for monomials. So like if phi 1, phi k are monomials in some polynomial ring O, then the sequence of being regular, so phi 1, the condition of being regular is the same as least common multiple of any two, phi I, phi j, is phi I times phi j for any ij. So in particular, right, so not one examples, but nevertheless, so x square, y square, z cube is regular, and x square, xy is not regular, right? K, x, y, z. So if this is the case, if I is generated by a regular sequence, then AT resolution of O over I is just a Koszul complex of I. is the Koszul complex. So in this case, it looks particularly very simple. So this module epsilon, which we describe here, so it should be symmetric graded algebra of some or module epsilon. So in this case, epsilon is just O plus epsilon 1. So the graded symmetric algebra is just S of epsilon 1 over O. And then epsilon 1 is just generated by E phi I. So I equal 1 K over O. So the generators of the module epsilon 1 are just parameterized by the generators of ideal, and then delta of E phi j, just phi j, right? Phi j 1. Okay. So what are other examples? In fact, there are not so many. So essentially, what one also finds in physical literature is the Koszul-Tate resolution together with some trivial complex. So let me just maybe say what I want to say. So what is trivial complex? Let's call it T. Is just sum of complexes of the following form. So let's write it, maybe n. So if we have complex of this form, 0, O, identity, O, 0, and we can have any direct sum of such complexes, you can shift the degree and so on. For example, here maybe just use another color, plus 0, O, 0. So complexes of this form, they're called the trivial complexes. And another example of Koszul-Tate resolution is just when you have a trivial complex, you can form A, which is S of epsilon 1. So we again, in the case of the regular sequence, just symmetric tensor product with S of T, where T is a trivial complex, some of the direct sum complexes that looks like the complex N. And then the total differential, let's call delta hat, is just delta plus differential of the trivial complex. And also in the original paper, so in Tate in the year 57, there is another example which I don't think I have enough time to describe it, but it's the case where there are two regular sequences. So also not a difficult construction where A is S of epsilon 1 plus epsilon 2. So there are two generators, two levels of generators. So degree 1 and degree 2. So it's the original Tate paper. And this is it. So no more examples are known, and actually we have a partial answer to why. So let me try now present our construction. So as I said, there will be Koszul-Tate resolution in decorated trees. So what we want to do, we want to construct this resolution A delta. So out of like two main ingredients. So first one, MT. So we just some projective resolution. of O over I. So here there is no symmetric algebra structure, just take any resolution of O over I plus some algebra of planar trees. So let me just give you motivation why we want this, why we decided to start with this projective resolution. So the reason being that in many cases it can be explicitly computed. So for example, so this Noether-Syzygy theorem says that if O is a polynomial ring in n variables, x1, xn, then there exists free, so not just projective, but actually free resolution of O over I. So for any ideal I in O, so for any I in O of length n, actually any finitely generated O module M will also satisfy. So or any finitely generated O module M. And there is a free resolution of length n. So it means that in a finite number of computations, you can actually find it. And so let me give you some working example. So the one which we will use to find the Koszul-Tate resolution for, but which cannot be found just in an algorithmic way, is of a finite number of computations. So we work with O, which is polynomials in 6 variables, x1, x2, x3, p1, 2, p3, and let I be ideally generated by n-geometry functions L1, L2, L3. So each shall I sum over ak epsilon ijk x xjpk. So just n-geometry means 3 dimensions. Then and this resolution has 2 generations. So at degree 1, so M1, so the resolution will be like this: O, 0, 0. Then M1 is just generated by E1, E2, E3 over O. So this is the free O module of rank 3, and of course the generators produce the n-geometry functions. And M2 has 2 generators. Let's call it F and F bar, such that GF is a sum of xi ei, and G of F bar for somewhere on I3 pi ei. So this is the module resolution. However, it's not a Koszul-Tate. So if one like just naively want to look at the algebra as of M1 plus M2, and like extend delta, extend G as a graded derivation, then actually it has 3 cycles of degree 3, which are not boundaries. So actually it's not exact, but we'll get into that. But you see, just module resolution, at least for some particular examples, can be easily constructed by hand, just by hand. Then what's the idea that we want to pursue is that we want to have some planar trees so the idea so trees decorated by M. So let me first describe the algebra that we want to have, and then I'll explain the motivation why actually we want to use trees. So first of all, let us consider the vector space of trees. Let's call it tree, which is just you just write all possible planar trees. So let me write it this. So tree, for example, like this, then tree of this sort, tree like this. Well, whatever you want. This. And so on, and also we add a trivial tree, which I write like this. So how do we refer to such trees? So we say that this is and this and this is the vertices, and this is a leaf. So you see, whenever I put this orange dots, I mean that the vertices of trees. Also, the vertex which is on the bottom of the tree, we refer it as the root, which is also part of the vertices. And also we have a trivial tree where there is just one leaf and no root and no vertex. So then, of course, let us denote maybe some notations. So tree N is a subspace of trees with N leaves. So tree K. So same thing, but with K vertices. And of course, tree N K. So N leaves, K vertices. So in particular, in the picture presented above, this one belongs to 3 to 1, and this one, for example, belongs to 3 to 4, right? And this one belongs to 3, 0, 1. Okay, so and the idea is that we want to consider the O module of decorated trees. So let's call it tree M, which we define in the following way. So it's just tree N and 1 to infinity tensor product is M, and this is M n times. So one invites you to think that the decorations are attached to the tree. So right, so we can write for a typical element as T tensor A1 tensor AN. So this is an element of n tensor M n. right? So then we want to equip this model of decorated trees with degree. So one says that degree of T, sorry, I just copy this. Degree of this tree is given by a number of vertices of T plus a degree of A1 plus degree of AN. So the degree that comes from the tree is just the number of vertices. So since, by the way, are there any questions up to now, or everything's fine? Okay. So then, since the Koszul-Tate resolution is symmetric, is a graded symmetric algebra, one expects that this graded symmetry must pass somehow the trees. So, and this is indeed the case. So let us define tree of M symmetrized, decorated. And the symmetrization will be in the following way. So if you have a tree, say with the let's say we have a tree where some distinguished vertex A. So let's just choose any. In fact, let us choose any vertex A. And suppose that so here's a root, something here, and suppose that from the tree A we have some C, A, B. So there is some decorated subtree that comes from the vertex A, and another tree like this. So T1, T2, tensor C, tensor T. So I want to be able to exchange them. So I want to be able to exchange the trees that comes from the same parent vertex. So I want to write following thing with some permutation psi. So I'm cheating a little bit, but I can just copy a tree, but it's convenient. So in here, I just want to say the sign -1, degree of C2, tensor C, tensor T, and of course T1, tensor A, tensor B. And I want to do the same equivalence for any vertex A of any given tree. Then this space of symmetrized tree of M would be just the quotient space of tree of M by this equivalence relation. So for any vertex A in vertices of T. So in particular, so let me explain an example what it means. So we identify tree of this form. AB is the same as -1 AB. BA. So I just use the tree and its decoration. And also for a tree, for example, of this form, ABC. For us, it will be the same tree as C, A, B, with a sign C, and here A plus B plus 1. So 1 comes just because there is a vertex, right? So A, B, they connected as a vertex. So now I want to equip S of 3 M with some differential delta and make into Koszul-Tate resolution of over I. So I still have not defined delta, but let me maybe before I explain delta, let me give you some motivation why trees. So why trees? Remember we started with the vector space of planar trees, and now I want to construct a very simple model. It would be just a resolution of a field K, but which would actually explain the construction of differential and also bring some insight on by using trees. So on the space of trees, so just let me go back for a moment. So remember, we have like all planar trees plus a trivial tree. So I define the differential in the following way. Differential, let's call it partial. So partial defined in the following way. So the trivial tree goes to 0. And the tree of this form goes here. And also I'll explain now how delta acts generally on any tree. But let me first introduce you a root map. So root map. So if you have any trees T1 up to Tk, so K should be bigger than 1. And they are mapped into T1 Tk connected with the root. So you see what you just do. You take a forest of K trees and then map it into just one tree with a degree 1 higher, right? So in fact, it's an isomorphism of the forest. Let's call it like this. So as greater or equal to 2, it just says that we take a polynomial degree of 2 and higher. It's the same as tree with 2 or more leaves. So this is the isomorphism given by the root map. So then I on trees with K greater than 1 leaves. Define delta recursively in the following way. So delta is minus root projection greater than 2. So projection, of course, on the forest, delta minus 1 plus root minus 1. And of course, prolong it as a graded derivation. So let me just briefly explain you how delta acts on trees. So delta of this tree. So let us do it very briefly. So applying root minus 1. So we get this. And if I do the second term, so I apply root minus 1, I apply delta to it, I get just 3 trivial leaves, and then I reroute them again. So to be minus these 3. And now the point is that if you take just the tensor algebra of trees, right? So the forest, sorry, here is not L, there is no symmetry, it's T. Tensor algebra of trees with this differential partial, actually it's a resolution of K, of a field K. So, and how to view it? So it's just one small exercise that one can show that partial partial root projection greater than 2 plus root projection greater than 2 partial is equal ig on 3 greater than 2. So you see everything that is degree 2, 1 or higher actually is all exact. So, and maybe so okay, like let's do like easy check for T equal RF. So let's say F is some forest, and we just routed them into 3T. Then if we apply the following thing, what do we get? We get just so the first term disappear to be root projection greater than 2 delta of root F. What is this? So let us apply delta. So it's root minus 1. So it will be root projection greater than 2 F minus root projection greater than 2 delta of F. Right. So, and what is this? So you see the term here. After I apply up to here, I have just a single tree. If I apply the projection, it just gives me 0. And the first part. So since we started with the forest, it's just root F. So indeed, for such trees, this is indeed true. So, and also one can, in a similar way, check on the forest that this is indeed the case, and it's just a degree 0 that there is a homology which is in fact just K. So we saw how the differential on trees acts, and in somewhat analogous.
Can I ask questions? Hi, Igor here.
Yes, yes.
Before you go on, can you just go through this action of the differential on trees one more time in this simple example?
Yes.
Yeah, so just a little bit more detail.
Okay. So you see. Okay, let me maybe just delete it then. So how do you do it? I do the following. So it's root minus 1 of this tree minus root projection partial root minus 1
okay,
of this tree.
You switch the order of the terms in the differential.
Yes.
Yeah. Okay.
Yeah. It doesn't matter.
Okay.
Let me move it a bit down. And then what is this? So root minus 1, I get this term minus root projection delta of this. Right. So and here.
Sorry, in the first term, the root minus 1, it makes sense because of this isomorphism that you wrote above.
Yes.
Right.
Yes.
Okay. So it basically like given a tree deletes the main vertex, and then whatever is left, that's the result. Yeah.
Yes.
Okay.
So now let's look here. So delta is a derivation, right? So it applies first to the first tree in the forest, and then to the second tree in the forest. If you apply to the second tree in the forest, you get 0, right? If you apply it to the first tree, you get just 2 trees again. To be minus root projection of 3 trees. Since the projection on the forest is the same thing, so you just have to reroute these 3 trees. So this is just this.
Sorry, and the projection map. Oh, can you say again what that is? The projection.
Yeah. So projection. Maybe write some other place here. So projection. So tree. It's goes to 0, and it's so sorry. Right. Projection corresponds to E0 on tree, and is identity on
the tensor algebra, the rest. Okay.
Yes.
And
Yes.
the reason that you can define the differential recursively, I guess it's because like so the term with the projection becomes 0 on trees that have no vertices, or so have 0 vertices.
Yeah.
Oh, sorry.
Yeah. So of course,
Just one connected. Okay, 0 on tree on forests that have one connected component. So it's non-zero only if you apply it to a forest. Okay.
Yes.
Right.
Yeah. So of course, I didn't check that delta squares to 0, but it's just an exercise. Maybe.
Okay.
I can check if you want.
No, that's fine. Okay, I just want to make sure I understood what the formula was doing. Okay, thank you.
Yes. So once this is done, so let me define, and you see why this was a motivational, although maybe a bit useless resolution of K. So now let us find delta on S of 3M delta. So how it looks like first. So in some sense, like I call it in the quotes, delta is G plus delta plus something else. So I want to combine the differential of the projective resolution. I want to combine the differential on the trees, and in fact, I need something else. And I'll explain now why. Now what, and then why. So delta on a trivial tree is just the of this tree. So for any A in M. Also here, like implicitly, I say that one F is just F for any F in O, right? Just to make sense. Secondly, so for trees, tree with at least 2 leaves of degree n plus 1, the definition is a recursive one, and it has 3 components. So so 1, 2, 3. So this would be one would be a component to the forest, And there will be a component again to the non-trivial trees with at least 2 leaves. And there would be a component into the trivial trees. So also I need here 3 projections for P1, P2, P3. Some from S3 of M into S greater than 2, T greater than 2, and that's for M. Right. So let me maybe write 3 of M. Here is this. So then, so delta, right? So then, what is 1? Is just root minus 1. So the projection to the forest is just unrooting map. A second one is a recursively defined one. So it's minus root P1. So P1 is just what was P greater than 2 in the previous context. Delta root minus 1. And 3, we just call this contribution minus psi, which is just an all-linear map from 3M plus 1 to N, which is actually recursively defined. And it will be explained later. So let me maybe first show you how this differential works before I explain it. So how does it work? So whenever you have support tree like this, A, B, C, maybe let's start with a simple one. A, B. So where does it go? So on root map A, B, then the second part is so you unroot, you apply delta, you apply projection to the forest, and then you root again. So in fact, this is where the differential acts on the leaves. So it will be actually plus, but rather minus GAB plus AGB. So let me be plus minus because it depends on the sign, of course. And also there is this contribution minus psi AB. Yeah, and of course for more complicated trees, it's more complicated. So, for example, if we take a tree A, B, C, that acts on this. So I will just solve this recursion. We just write you a solution to this recursion. So the answer will be A, B, C minus psi contribution of this tree, A, B, C. Oh, plus minus this tree A, B, C. So you recognize the differential that comes from the tree part. There will be also some psi of A, B, C. And then there would be, of course, the tree part that comes from the differential on M. The A, B, C plus minus A, G, B, C plus minus A, B, D, C. Yeah. So I think what I want to say now is like what's the meaning behind this behind this map psi. So yes, does look like I have too much time to explain the differential. So let me just demystify the map psi and then give example. So in fact, this data that one constructed is a homotopy tract onto the initial resolution MD. So what do I mean? So use white is more visible. So this data, so the symmetric algebra with differential delta. So here are P1, and here is this. So in fact, what one constructs here is the following data. So the inclusion I just goes in a simple way. So our I goes to a to trivial tree tensor A, F goes to F, for any I M, for any F O, and projection part. How does it work? So also one tensor, trivial tree tensor A goes to A, F goes to F. For this as well. Then for any tree T A1 AN in a decorated in a symmetrized decorated non-trivial tree, actually P of such tree it's 0. However, once we have several such trees, so P of T1 A P up to Tk T T. Here K is greater than 1. It goes to psi and the routing of these trees. So if we root this K trees, T1 A P to Tk C T. So in particular, if you have tree like this, A, B, so where does it go? By projection pi, it goes to psi of this tree of AB. So what does it mean? So actually this map psi is just the induced multiplication. So on this symmetric tensor algebra, we are easily equipped with the multiplication, just a symmetric tensor product. However, we can take two elements of the modular resolution of this resolution MD, projective resolution. By map I, we map them into the into this Koszul-Tate resolution and take a multiplication and then send them back. This is what this map psi in fact does. So I mean, in particular, so if one finds all such psis, one also gets MD equipped with infinity structure, which I mean, in the example that I discussed is particularly simple. So let me maybe say just a little bit about example, which was here. So let me maybe here. So here, right, we have the data of the resolution, and so then of course tree of M is just modulo trace of the form. So E1, E2, E1, E2, E3, right? And one can do whatever you want, F, E1, E2, and so on. But the only thing that is missing to construct the differential is the map psi. And here it looks particularly simple. So psi is for degree reasons, psi non-zero is only on 3 of this form, EIJ, which is just epsilon ijk x k f bar minus pk of f. So what is this? Is one can view it as a multiplication. So we in like ei star ej. So the resolution of over I in this case admits a multiplication which looks like this and is 0 in other cases. So let me maybe just try to say a few words about the application. So what this resolution is for. So first, of course, you see when you just find this multiplication, there you have it. There you have the Koszul-Tate resolution. However, this construction also proves useful to find whether so natural question one can ask for the Koszul-Tate version is whether this model epsilon has finitely many generators. So if it is, then maybe you can just forget what I just been talking for an hour and construct Tate resolution just by hand. But if it's not, then it's an indicator that just naively constructing Koszul-Tate resolution, you're not, you're getting nowhere. So in particular, so for any, so let me just spell out what I want to say. So for any Koszul-Tate resolution S of epsilon delta of over I, let us define the reduced complex. So I don't have much time, but let me try to explain. Of over I delta for any ideal J is inside O and I. So this is the complex of the following form. So epsilon I tensor modulo J, epsilon I minus 1 tensor modulo J, and so on. So the differential is just comes from the Koszul-Tate differential, just the linear part, right? You just project on the linear part and the tensor product with the following O module. And what one can prove, in fact, that the homology of this complex, that H of RG modulo I delta underline delta does not depend on the choice of the Koszul-Tate resolution. So in some sense, what you can say is that if by chance you find a representative at any degree, right, then you can say that the epsilon has infinitely many generators. And it turns out this is indeed the case in the following. This can be done using this arborescent, using this tree resolution that I described today. So yes, maybe to say the results. So like using this tree construction, one finds that epsilon has infinitely many generators, in the following cases. So case 1, so if O is polynomial, I is generated by a non-regular sequence of monomials. So we found this result only for monomials at this point. So, for example, x squared, xy is at cube, right? So if this is the case, then epsilon has infinitely many generators. So the Koszul-Tate resolution, I mean, it's almost all the time has infinitely many infinite lengths, but also, right, one just constructed step by step infinitely many computations. So no way. And the second case is if image of psi belongs to Jm. So this is in some sense this condition is not really clear, but at least for some examples one can just check it. And in particular for the engeometrum example, it is the case. So I can just take a J ideal, which is just any generated by x1, x2, x3, p1, p2, p3. And this is the case, and yeah, so the epsilon has infinitely many generators. And how one does it, I'll just maybe say a few words. So if let's call it E1, E2 in this example. So this tree construction gives you a particular cosine, gives you a particular cycle of the form E1, E2, E2. And here is .E2, which indeed belongs to the H of the reduced complex. And it's, I mean, once one is familiar with the tree construction, it's easy to check that it can be, first it's closed under the delta bar, and it cannot be exact. So at least this can be deduced from this construction. So I think I don't have any more time, so thank you for your attention.
Thank you. Any questions? Igor?
Yes, first I was just clapping, but I do have a question. So with this construction, so I understand that you can generate so given a module level resolution of the ideal, you can generate the Koszul-Tate algebra resolution. But can you formulate some criterion for when the Koszul-Tate resolution can have finitely many generators?
So criterion, I don't. So criterion is I don't know. So I know the case that like, so if the O is noetherian, I is regular generated by regular sequence, then it's Koszul complex, right? And that's basically it. However, if it's a non-regular sequence, so as I said here, we managed to find only for monomials, unfortunately, that it's not finitely generated.
But in the case, in the regular sequence case,
yes.
So how does your construction reduce to the usual Koszul complex, right? So how can you show that you can eliminate any generators and
yeah. So yes. So in this case, if it's a regular complex, so there is some, let's call it ideal, I don't know, what's the good letter? Maybe A, which is just take all 3 of M, and also any trees of the form A B minus A minus A star B. So if you take this ideal over S of 3 M, if you just quotient it out, you get the Koszul complex.
Okay, so for this ideal, you somehow can show that it has a contracting homotopy or something like that.
Yes.
Okay. Okay. All right. Thank you.
Other questions? Maybe so. My question may be kind of generalization of this one. So what you get by this tree construction in general, it's not a minimal resolution in whatever sense, right? So
yeah.
There might exist some minimal resolution, and then how these two would be related. I think it's a generalization of what you explained a minute ago.
Yes. So there is indeed there is a definition of minimal resolution. So if O is local, so there is also for polynomial case, but I mean graded polynomial case, which is somewhat the same. So if O is local, so you have maximal ideal J, only one, then like minimal resolution is dm is inside gm. Yeah. However, we have also a definition of minimal Koszul-Tate resolution. There it will be, I think, the delta of epsilon belongs to J epsilon plus S greater than 2 of epsilon, which is the minimal in the sense that if you construct step by step, this is the minimal Koszul-Tate one can get. It also satisfies this condition. Yeah. So, however, this tree construction is never a minimal one. So you can see, because whenever you have a tree like this, there will be always term ABC, right? Plus something. So it's never in the, so the coefficient here is invertible 1. So it's like 1. So it's never in the maximal ideal. So this construction is never minimal. So you never get this resolution from just naive algorithm when you just compute homology at each step and just kill the necessary cycles. Yeah. So, however, I mean, the plus of this construction is that in a number of cases, it's done in finitely many steps. You just need to construct all these operations psi. However, for the minimal case, as example for monomials and non-regular sequence, it's infinitely many computations.
If the sequence is regular, what is the minimal resolution? Is it Koszul?
Yes.
Okay. So other questions?
Yes, Sasha, sorry, I missed the first few minutes of your talk. Maybe you already said this, but are these results written down somewhere?
No, not yet, unfortunately.
Okay.
So I hope it will be soon, but not yet.
Is your PhD thesis available online or not yet?
No, that's the point. That at least the reason was that the paper should come first, then the PhD. But you see, it came the other way around, and I think it would be better to wait for the paper, and then I can upload the thesis.
Okay.
Okay, looking forward to it. Thanks.
So this is a part related to your PhD thesis, right?
Yes, yes. Yes.
Okay, any other question? If no, that we should thank the speaker again for the interesting talk.
Let me